And the title is Hazard, Risk and Reliability in Geotechnical Engineering. Just have to keep track of my time here. And in 2015, it was not that spread using these methods. So the lecture started by saying there are three basic questions. How can reliability and risk concept help to ensure adequate safety while achieving cost-effective design? And what are the advantages and challenges of the hazard, risk, and reliability approach? And then the third question, why aren't these methods used more widely? But they have been, times have changed and they are used much more widely today, so we'll skip that part of the lecture. And there were a lot of skeptics in the room. First, the Rankine lecture is just a lovely occasion. You have 1,000 people in this enormous auditorium listening to you, plus another 800 in an overflow room, and it's very formal, with a toast to the Queen and all that. But it's really very lovely. So when you're asked to go and give the Rankine lecture, say yes right away. So the strategy I had in answering this question was to present examples that are so convincing that they would make the audience want to use some of the methods, and show that these probabilistic methods, together with deterministic analysis, in many cases are necessary complements to each other. So the contents of the lecture is first a little bit of basic concepts so that we all agree on the terms, and then the example of reliability analysis that ensure the adequate safety and lead to cost-effective design. So I had 4 of those case studies, and some are short, and then show you the importance of such method to really tell you what does the code tell you when it tells you a safety factor would be 2.0. It does not necessarily mean that it's as safe as another code that says the safety factor should be 1.5. And then the conclusion. Then Theo asked me to give a few personal career insights, so I had prepared them, so if we have time, we can look at that. So just basic definitions so that we agree. I mean, when I mention risk, we all understand the same thing, because risk has very many meanings depending on which field of expertise you are working in. So in our engineering point of view, it's a function of the hazard and the consequences. And the hazard is the probability that something will happen. It could be a dam failure, it could be a slope failing. The consequences are a function of the elements at risk, like persons or buildings or roads, and their vulnerabilities, how sensitive they are to a certain flow of water coming down, and their value. And I've put an example there. It's a landslide in Munkedal in Sweden, where it was due to the contractor not adhering to what was the protocol. But you can see it has disastrous effect. The entire road completely disappeared. And it was on Christmas Day, naturally. And to illustrate the concept of hazard and risk, I have this illustration here. First you have, this is an area in Norway. I didn't get the pointer. Whoops. I'm just trying to get the pointer. There. You have an area in Norway where there's some people living, and here's a slope. And the area is on some very soft clay, quite sensitive, so it behaves like a contracted material as you have in your TSF. So an area with high landslide susceptibility or hazard, but there's nobody living downstream. So the risk is small because there are no consequences to a landslide occurring there. And then naturally everybody wants to earn money, so an investor can say, yeah, but this is a nice area. We could build lots of apartments and sell them. So stabilization was done over this entire area, and buildings were built, that was in 2007, to reduce the hazard of a landslide. Then all these buildings, new buildings are in place, and the area is very flat, but that's very typical for the valleys in Norway. But because the hazard has been reduced, the area is developed further, but by how much the hazard was reduced, we don't know. And the consequence became much, much bigger because there were many, many people living, and this is the slope that was before. If a landslide should occur, there should be a very high risk. And this is what happened on the 30th of December 2020, where the new area that was built at 4 o'clock in the morning began to slip, and then 11 people died. Early works of the aspect of risk and uncertainties, 1966, Peter Lund in Hong Kong. He started describing soil as a function, soil properties as a function of their uncertainty, looking at the mean, the standard deviation. And he suggested, based on what would never fail, a suitable value of probability of failure for design, bearing capacity, should be 10 to minus 4 to 10 to minus 5. He did not specify whether it was per year. At that time, the science was not that advanced. So I believe it may be for the lifetime of the structure he was talking about at that time. And then Wu and Kraft in the United States, they looked at the probability of foundation safety. That was in the 1970s. It's a long time before this Rankine lecture. And they looked at excavation, slopes, settlement, and they concluded that the factor safety is not a unique quantity. So when you do a risk-based analysis, you're really doing the same thing as what you do in conventional analysis. Let's say that we're calculating, we have soil properties, loads, and drainage conditions, and geometry, and let's say we're calculating slope by slope. There's equilibrium of force. You use a model, limit equilibrium, you can use finite element, and then you calculate a safety factor. And the acceptance criteria is this safety factor shall be greater or equal to what is prescribed in the codes. When you do the probabilistic or risk-based, as it's called today, you do exactly the same thing, but the input parameters are different. You describe the soil properties, the loads, geometry, if it's uncertain, with the distribution. It has a mean standard deviation. So instead of just one value, it has a multitude of values, or it can have a multitude of values. You have a model, the same model as in the previous slide. It's an idealization, but it also includes an uncertainty. So it has what is called a method uncertainty or a model uncertainty. And then when you do the calculation, instead of getting just one nominal value for the safety factor, you get a distribution, which can describe what we call the safety margin. The results we obtain is a probability of failure, reliability index, and then ideally, we should compare that to acceptance criteria, which we'll talk about a bit later on, because not all countries and people agree on this. And this is a very classical drawing I must have shown many times. I think the first time it was published was in 1986. There is no direct relation between factor safety and probability of failure, but there's a way to illustrate how they depend on each other. And this is a situation, or the first time we realized that it was a pile design, and after it was for a slope. If you have a safety factor of 1.4 and very little uncertainty, then the distribution of safety factor would be like this tall and slim distribution. But there is a probability of failure, there is some combination of the loads and the resistance that can give a safety factor less than 1. So this is your probability of failure. If you have either not another site or the same site, but you calculate a safety factor of 1.8, 1.8, but you have a lot of uncertainties. You have largest, the pore pressure, the soil type, the friction angle, or the undrained shear strength, then the distribution of the resultant safety factor becomes what we call much more diffuse. So it's squat and flatter and wider. And then look at the zone. The zone where the safety factor can be less than 1 is much bigger. So a lower safety factor can give you a much lower probability of failure. In this case was 10 to the minus 4 per year, whereas the one with the safety factor 1.8 gave 10 to the minus 2 per year. And this is not something I prepared for here. It's a situation we had for an offshore platform where we had to recalculate the safety because the platform had been hit by a boat. So just came in handy. When we saw the high probability of failure, then a whole new site investigation was done. But through regulation and tradition, the same value safety factor is applied for a slope or pile design with the small uncertainties and with high uncertainties. So this is not logical. So that's why the risk-based analysis take into account the uncertainty and the distribution of the safety factor are more complete. But they should not ignore what was done before, but it adds new information. One thing also, so often when I talk with clients, they think that there's a way of making that the failure probability, this small zone here, is zero. In our world, where we have uncertainties and we're not able to put the borehole every single centimeter, and we're not able to completely describe the soil on a fairly large site, it's nearly impossible to have a failure probability of zero. And I don't say much about regulation today to make it shorter, but ISO, International Standard Organization, Australia is part of it because I work on writing the codes and we have some very good Australian people working on this. And they define the risk as risk is the effect of uncertainties on objective. And although that's unusual language for us, it's very true. It is by how much the uncertainty are going to change the safety factor you want to achieve, or by how much the uncertainty would cause the failure of a dam. Then just 2 slides or so how do we describe risk. And qualitatively, often, it's not the only way, but it's a risk matrix where we have a hazard category or the probability that an event may occur from 1 to 5, and the consequence category from 1 to 5. And in this matrix, you bring in the events that may occur. For example, if you have a slope, and then if somebody makes an excavate, and then you lose some of the toe, how would that influence the hazard, and what are the population that are at risk or the infrastructure at risk? Then the user decides which zones are low risk in green, which one are medium risk in yellow, orange, and then what is high risk. And here I show you something perfectly symmetrical, but usually it is not symmetrical. But what I've realized, when I started with the more complex analysis, that even doing this kind of analysis, the discussion it brings in, it first brings everybody. It's usually done in a workshop or so. It brings everybody on the same foot, and then they discuss what could happen, what could not happen, and how many people can be affected. So even the simplest methods, they provide added insight into the safety and what are the important factors affecting it. But how can we describe risk? We often use a diagram when we're talking about numbers. And this is somewhere where people don't necessarily agree, so it's one of our challenges. But this risk diagram, it's a series of temporal probabilities, probability per year, and consequence. It's called FN diagram. And the vertical axis is the annual probability. It doesn't have to be annual, but it's some kind of measured probability per time. And here's a consequence. It's number of fatalities, or it could be cost, it could be time for restoring the destroyed road or a bridge or such. And you usually define this diagram into 2 zones, risk that is acceptable in green and the risk that is unacceptable. Now this is what people don't necessarily agree. Some people disagree that we have rules or guidelines. Some people disagree in the way where you make the division between acceptable and unacceptable. But in this gray zone here, I've put in the regulations, the guidelines in 10 different countries that are well published and now starting to be well known. And it gives a range, which is very interesting, that for example, one fatality is between 10 to minus 2, 10 to minus 3 per year. 10 fatalities is an average about 10 to minus 4. The line in the middle, yeah, most of these guidelines are in general or are specific for dams, mainly water retaining dams. And the line in the middle is for the man-made slopes that was developed by Hong Kong. And you know Hong Kong has many problems with slope stability. It's not for a natural slope, where the probability will be much higher, but it's for man-made slope, one that has been grouted or has been reinforced and such. And naturally, we won't go into this, but when there's a very, very large number of consequences, special studies are made. And what is acceptable, I'm not going to propose something, but I'm going to just give you a dimension to compare it with. I mentioned 10 fatalities, 10 to minus 4 per year. These lines are called societal risk. But when you analyze one failure mode under an earthquake, that's the probability of the first person closest to what event you're looking at will be killed. So that's what we call an individual risk. But here we have an individual risk. Yeah, individual risk is along this line here, one person. And I just put the statistics of Canada of what is your hope of living based on statistics. Including all the causes that may cause the death of a person. The numbers are very similar in the United States, very similar in Norway, and I have also seen the numbers in Australia, and they're also very much close to that range. But what this tells us, that the safest time that you are alive is when you're between age 5 and 7. This is age in this axis here. And the probability that you may die due to all causes is 10 to minus 4 per year. It's not lower than that. And then as you grow older, unfortunately, some of us do that, then the probability of dying in the next year increases. So we can take somebody 90 years old, I'm not there yet, then the probability of dying the next year is 10%. And if you think about it, naturally it makes sense. If you're older, you might get sick more frequently than the vigorous 40-year-old. If you're 60 years old, it's 1% probability of dying due to all causes in the next year. And you can see that the arrow move. The target of 10 to minus 4 is here at the age of 10 years. So I'm not saying it's exactly a proportion, but this is individual risk, and on this line, individual risk is 10 to minus 3 per year. So it's one level lower. So those are the basics. I'm going to tell much more on the basics. And I'm going to look at these 4 case studies. And they're all real cases. It's all analysis that we had to do, or that other people did, in which we got the documentation for. And the first war is for offshore installation, and it was for very big jackets. And the problem occurred in 2013. I had just stepped down from being director at NGI, so I had plenty of time. So they asked me to look at this. And those are very large structures. Why it came, the first case is the deterministic analysis said the paths needed to be 90 or 107 meters long. Well, we can't drive paths that long in the North Sea. And there's a lot of problem associated with driving in such long paths. So the motivation is that the guidelines require the same level of safety for the CPT-based method for power capacity as for the older API method. The most frequently used also in Australia is the API method, American Petroleum Institute, and the CPT methods, therefore, at that time, new methods that were used, but people did not know how to choose a safety factor. So it's the same factor safety was given. And we all thought, well, the CPT method gives you continuous profile, you have much less uncertainty. And what the code said, the designer has to select an appropriate safety factor when using the new CPT method. What is appropriate? And so the designer, he can choose to be conservative, apply a high safety factor, or document the safety level, and that's we suggest doing this with probability approach. And we won't go too much in the theory, but we use load and resistance factors with pile design, and it's an equation like this. These are the loads, the static load, the weight, and then there is the environmental load, which is due to the wave, and on these we apply what is called load factors, and then the sum of the load should be less or equal, a favor, to the ultimate resistance. And also, this is also reduced by a material factor. That is standard practice. It's called partial safety method. So, what we're going to look at, we're going to look at what is the necessary gamma n and the resulting safety factor probabilistically. So, at the same time, it was for the energy company called Statoil at the time. In Norway, they were building jackets of very large size at 3 sites. I can't name the sites, ABC. 100-meter water depth, and you can imagine 100-meter water depth and having 100 meters of pile underneath. There were piles, big things, 2.5 meters in diameter. And then the wall thickness also is not negligible. And the governing was the loading and compression, so this makes it easier for our presentation. We will not look at tension. And the 4 newest CPT methods, which had just been included in the code in 2005, but you know how it is. Each proponent are part of the committee, and they did not want to prioritize among the methods. We said, well, you can leave the NGR method out if you want. But okay, all 4 included. The Imperial College method, the NGR method, UWA method, and Fugel. And I must say, UWA was doing a lot of the hard work, and were one of the prime motors pushing for this acceptance. So we got accepted that we introduced CPT method instead or in addition to the API method. Material factor that was used is 1.5. Or they call it resistance factor, so it depends if you're using the English code or the Australian code. And for probabilistic analysis, we did some analysis setting a target, an annual probability of failure 10 to the minus 4. So the failure probability should be lower or not more than 10 to the minus 4 per year. And this is the no-shock guideline. That is what is used in Norway for offshore design. Norway is quite advanced in offshore design for an offshore installation. So in my case study, I have different methods, so I explained a bit on the method before I pursue. So in this case, we use what is called a first-order reliability method, and I try to explain it here. And this is where we define what is called a performance function, and in this case, we said, well, the resistance minus the load must be greater than 0. So if it's greater than 0, then the performance is satisfactory. If it's less than 0, you have failure. And if you have 2 parameters, one is resistance, one is load, then this pink zone is what we call a failure domain, and the blue one is the safe domain, is where the performance function is greater than 1. Now they're just 2 variables, but you know the resistance is friction angle, it's a resistance, it's unbraid shear strength, there's the unit weight, there's a number of parameters that come in there. But in just these 2 parameters, the surface may look something like that. So, and each of these uncertain parameters are what we call a random variable, where you have a mean, a standard deviation, and a distribution. And just a little bit more in the theory, that's the last one. When you have 2 parameters like here, once you put all the parameters together, maybe it looks like some kind of pretty surface like this. But you know, when you have 5 layers and 5 parameters each, then 25, then you get something very complex. But the computer does that, you don't have to worry about it. But what we do is we do the analysis and find the distribution of safety factor for all the variation of the random parameters, and you define a zone which is unsafe, where safety factor is less than 1, and then the region was safe, and through statistics you do a transformation of this into a normal distribution, and then theoretically, lo and behold, the distance between the surface, between the unsafe and safe design is called the reliability index and is related to the probability of failure. Easy to calculate because of normal distribution. But you don't have to go into the details because that's a black box. It's like running Plex. It says you say what the parameters are, what is the uncertainty, then you run, you say what is the equation you want to calculate, you run it, and then you get the result at the end. So you don't have to go through all this as I showed. Okay, so here was the first site, which is what we call a clay site, and the underlying shear strength versus depth. The blue line is 0.25 times the in situ overburden stress. Here you have the underlying shear strength. It was mainly based on lab tests and a few CPTs with depth. The value of shear strength is what's in red. And in those days we called the strength I going to use for design characteristics. That's the black line. The mean is the red line. So when you do the deterministic analysis, you use the characteristic. When you do the probabilistic analysis, you consider the entire range of variation of the measured shear strength. And just for interest, all the data is what is in red, so there's something stronger here. But I showed you what the first profile of underlying shear strength that was proposed, and this is the black line. Why this was so low, I'm not quite sure. Here. And then all of this. And to me, a profile has to be logical. So why the strength decreases by so much at this level? Okay, that was just for interest. So, but in the probabilistic analysis, we use a distribution like this, sometimes normal, sometimes log normal. What was the best fit for the data? Site 1. And site C, which was called the sand site, you had a bit of clay in the top, and these are cone resistance rather than the underlying shear strength, the other one. But you see how variable the soil is. Well, that's not so easy to see. But you can see the data here. Naturally, when you have a lot of CPT data, all of this is reduced and cleaned up and averaged with a computer program. But what's interesting in this sand, this value here, a little bit bigger blue, or no, purple here. Purple is when the CPT reached maximum capacity. So the strength, in fact, is higher, but the cone cannot sustain more than that. And that's what I call the PQC in the sand. And then we had a site that had more variable soil, like this one, site B, which is a mixture of sand and clay. And we didn't plan it that way. It just happened that way, and they had 3 sites that were current at the time of the work. But here what I'm showing the difference in the calculated actual pile capacity with the 5 different methods. The first one is the current API. Now, in sand, we know that the API method is no good. It's accepted by all professionals, so it's much too low in dense sand. And here's the range for the 4 CPT methods. I'm not saying one is better than the other, but there's quite a bit of variation, as you can see. It makes a difference if you want to design for a capacity of 100 meganewton or 175. It means a lot of money. Another product that this analysis gives us is the importance of each of the parameter in the analysis. This is just for information, but in the one case here is the model uncertainty was the biggest contributor to lowering the annual failure probability. Part of the work also, the Statoil was so generous that they said we were allowed to make a database with all the pile load tests. And this was done by UWA. It was Barry Lehane, who did this in cooperation with us. So we had many students going through all the pile load tests in the world and then setting criteria and choosing only the ones that were reliable. And this is one of them. It was looking, you can see we had one load test at this depth, and then what resistance was predicted by the 5 methods at that same depth. And the agreement wasn't bad, but it wasn't exact either. And this was the soil profile that was used. But this is all good work by UBA. So in our calibration, what we did, we calibrated all the model tests, but after that we had 16 sites, not just the 3, but we started the 3 and then we added more sites. The sponsors were allowed to provide 2 sites each of them, so that was good. So we had the distribution of the load, maybe it looked like this, and the resistance maybe looked like this. And this is what we're interested in, what is the probability of failure, and what should be the material factor for it. So a calibration was done statistically, and I don't have to go into detail with this, but we spent more time in looking where the measured capacity compared to the calculated were less than 1, because this is where we were over predict capacity, and that is where is more dangerous in terms of the pile failing. And you can get a fairly good fit here, and then we had the mean, the standard deviation, and the distribution were often Gumbel or log normal. And here I show you the calibrated resistance factor relate to the ultimate capacity for the target probability figure 10 to the minus 4 per year. We kept the load factor on the wave loading as constant at 1.3. It's very difficult to vary the two of them at the same time. And for the 3 site, the clay site, the sand site, and the clay and sand site, then you have a comparison for the 5 methods. And we don't have to spend too much time on the values. We can see, well, let's not take the NGI method. The current of PI was to have 10 to the minus 4. You had 1.35 in the clay, 2.36 in the sand, and I mentioned it's not a good method. And for the clay and sand, 193. So, which is very different from the 1.5 that is in the code. And we can take the UWA method, that's very interesting. It was not, it was introduced after the site A was finished. It was 1.55 for site B and 1.50. So there it is much more consistent, constant. And the requirement is 1.5, so good for the UWA. And for example, the Imperial College, 152, 145, 132. But you see that they vary, they don't move consistently in a different direction. But the conclusion, the Moorsock allowed us to design the pile as a function of the target of 10 to the minus 4 per year as failure probability, rather than using a constant safety factor. And the result was as this. The consequence for the required pile penetration depth at the 3 site, for the clay site, the pile length could be reduced from 90 to 75 meters. At the site B, 51 to 27 meters, it was half in the sand, but that's because usually one used the API method, which is much too conservative. And then the site C, mixture of clay and sand, the reduction was much less, but I think it's because the compensation of the errors and the uncertainties in clay and sand, 45 to 36 meters. So the reduction in deterministic pile penetration depth was possible because it's documented that the probability of failure less than 10 to the minus 4 per year, which is a rule in Norway. And I'm not allowed to write it, but the client allows me to say it, and just at one site, they save $40 million just on the operation and the pile length, buying the materials. But then also you have to think that all the complication of driving piles 90-meter longs for days offshore the North Sea, it's not easy. It's always bad weather there. So it was a very, very big plus for the company. So for each case study, I have the closing slides of the added value of the reliability analysis. It was the probabilistic design with a target of 10 to the minus 4 per year resulted in very significant savings compared to the deterministic design with the traditional standards. The reliability approach allows one to design with a uniform margin of safety and to calibrate the safety factors prescribed in codes. My last example would be the calibration. The newer CPT methods are more reliable than the API just because they're continuous. You have data continuously. The API, it's based on a number of shear strength from a laboratory test or on a correlation as such. What is interesting is the results are most affected by the model uncertainty or the method used to calculate, especially for piling sand in sand. That's why the API method doesn't work. But so it means if we want to reduce uncertainty, we have to work on acquiring more confidence in the models that we use. The second example is debris flow in Barcelonnette in France. And it's quite short, but we have a catchment called a Faucon catchment, which is up here. And it has had repeated episodes of landslides or debris flows. And there's a village, Barcelonnette here, there are a few houses here, and it is the path of the earlier landslide. And the question, there's a point A and point B, which we will discuss later, is the question of what is the thickness and the velocity of the debris if the landslide reaches the village, because it tells you something about how many people may die. This was a semi-type A prediction. Landslide had occurred before, but the person who was doing the analysis together with us was an NGI, a postdoc fellow, as we call him, and then he did not know about the results. You know, he did not even understand French, so he had to do his analysis without having seen the results. The method that was used here was Monte Carlo simulation, whom I'm sure you all know of from your high school years. And there's something funny in my slide here. But there was some earlier analysis and which told us that the model, the viscosity model for this material, the best one was called Wolmin-Bingham. And that's an equation how the material moves. And so we introduced each parameter as being a random variable, and that also forms a funny looking surface in space. And then we did 5,000 Monte Carlo simulation, calculating the velocity of the material moving and the debris from the volume that comes from the catchment as it spreads down. And then what we obtained a distribution for either thickness or the velocity. And I'm not saying anything more. Jose Cepeda did this work. Unfortunately, he doesn't work in geotechnical engineering anymore. And here is the observations of two landslides, one that occurred in 2003 and one in 1996. Yeah, this one you see well. And these are the results of the Monte Carlo simulation. The blocks in here, if you use the Monte Carlo simulation, you get another distribution like this. And this was the best fit, which ended up being a gamma PDF. Why we do that is because it's a way to calculate values. And this is the debris thickness in point B, the lower one. And then another calculation, but this is the velocity, also in point B. And the best fit was also a gamma. It's not quite as good as the previous one, but it's still okay. And with the comparison, the two landslides that occurred before. And you can see that the peaks, or the mean values of these distributions are quite close to what was measured. So the added value of the Monte Carlo analysis, Monte Carlo is an excellent tool if the mean and standard deviation are the main interest. For modeling the tails of the PDF, very low probability of failures in other words, one needs a very large number of simulations. So depending on what we put Monte Carlo, this was quite a complex equation, and when we put Monte Carlo on top of the two-dimensional and three-dimensional Plaxis finite element analysis, so those are quite complex. Then if you do more than 1,000 simulations, it takes a lot of time. But I did one analysis with, I think it was 49 parameters. So what I did is at 4 o'clock, you stop working at 4 o'clock in Norway, you put it in a couple of machines, and then you let it run all night, and when you come in the morning, then the results are there waiting for you. And then you do that every night. And this Monte Carlo analysis can be used to experiment and validate calculation procedures. So in 2014, at the time of the lecture, we had used Monte Carlo to simulate strain softening in clay, because we have a lot of quick clays in Norway, to account for the strain softening by using a multitude of repetitive analysis and seeing how the safety factor varied with this strain softening. The third case study is a water retaining dam. And again, I try to make it short. It's a series of dams in Norway, Neshamn, and for some reason it's clear here, but it's not here. But the main dam is here, but it has 6 saddle dams, other smaller dams, to either act as spillway or to provide some retainment and such. It's zone embankment dam. The big dam is here, and then the smaller dams are here. Rockfill dam. It also has a concrete dam, and which acts as a spillway, an emergency spillway, and then analysis were done with the first order reliability analysis to check the stability at the bedrock, but I will not present that. But we use here the technique called event tree analysis, and I discussed that quite a bit during the workshop, but it involves inspection of the dam, and then you make a big list of all the possible failure modes that could happen, and then you prioritize among them. You construct an event tree, which I will show you, and then calculate probability, evaluate the results, and you always do an iteration or two. And this is also done with a group of experts, and today we don't call them experts, we competent people. The people with the right competence, we say. And what was written by the guru of this method, which is Steve Vick, is the collective judgment of experts, structured within a process of debate, can yield as good an assessment probabilities as mathematical analysis. He wrote that in 2002. He was a classmate of mine, and he's very pragmatic engineer, and there's also an expert on TSF. So the event tree looks like this. You have an initiate event, like an earthquake or a flood, and then you find out what happens if, for example, my spillway is blocked. And then there's a technique to calculate probabilities. And this can go up to failure and consequence. And here's a textbook example. The event tree analysis is in the book by Hartford and Becker. And it's, if the example, you say what happens if you start the earthquake hits your structure. And that's in this case we took the 100,000 year earthquake, that's 10 to the minus 5. And then it's very simple. You ask, are the gate functioning? Gate closed and inoperable or gate operable? And then you assign a probability for that. And often that's by experience. I will come back to how you get those numbers. And if the gate are closed and inoperable, then the next question, are you losing control over the reservoir? You lose control of the reservoir, yes. You don't lose the control of the reservoir. And then you ask the question, will my dam fail? And then you have to assign the probability of the gates being closed or the gates being operable. And there's a lot of engineering judgment in addition to data that comes in this. But in this event tree, the events of the node should be defined such that they are mutually exclusive and cover the whole range of variation. So, for example, gates closed or gates operable, it's one or the other. And those are the only two options that you have. The probability of failure is a function of the product of this times this times this times this, very easy. How do you obtain those numbers? You obtain it from the statistics based on observation of test results, like all dams have statistics on the water level or the tailings level as a function of time for the past 40 years or so. The calculation of the geomechanics model, for example, calculate the safety factor of the embankment is 1.4. That's lower than so that tells you that maybe the safety is not as high as it should be. And then expert judgment comes in to evaluate experience. And another rule, the probability estimate should be based on a demonstrable chain of reasoning and not on speculation. Consensus is achieved through discussion using a standard description of uncertainty. So the example for Nation, I'm not going to read all of this, but these were the potential modes of failure that were discussed. There were many more, I just took the ones that were most important. And you look at the weaknesses in the dam, like internal erosion, landslide in the reservoir, if there's a mountain out there that might create a flood wave, blocking of spillway, operation, people not doing their job correctly, aging of concrete. And there can be external triggers from precipitation, glacier melting in Norway, hard packed snow blocking the spillway. Climate change has to be accounted for one way or the other. In Norway we have the problem for ice loading, and then earthquakes loading and such. And I just added this one, meteorite or airplane crashes, just to say that also the most improbable things are discussed, but they might not be prioritized for analysis. We also have sabotage and such. But it's funny, one of the dams are analyzed in 2021 during the pandemic, and so it was done online. A plane had crashed in the reservoir. So it does happen. So we're not going to go into detail, and you can't read it because somehow the projector doesn't give what I see here. But this is analysis for erosion, and you ask the question, does leakage occur? And is the leakage self-healing? It's a function of the type of filters and the materials we have in the embankment. Is the leakage discovered? Some dams are instrumented, some are not. Some are well instrumented, some are not. Some are continuously, some are just haphazardly. And okay, if the leakage is detected, if yes or no, you have different ways of going. If it's yes, then you can ask first if you have destructive erosion, and then if you are able to repair this erosion in time. But if you don't discover it, then it's just you don't have remediation, so you have destructive erosion. And then it brings you to dam failure. Then you can have the consequences and such. And then the probability of failure is the product. It's not easy, and it's not an exact answer. There's a lot of engineering judgment, especially with internal erosion. But when you're doing earthquake studies, you have a finite element analysis of the earthquake and the sediment that will occur, and whether liquefaction will occur, so you have more data to use. But for this Nation dam, these were the annual probability of failures that were calculated before rehabilitation under internal erosion, flood, earthquake, erosion, the rock foundation. That was an important case because we've had 2 failures like this in Sweden, so therefore we always think about that. And we also calculated the total failure probability, which is the sum of the probabilities for each the failure mode. And in this case, before rehabilitation, we had 10 to the minus 5, 8 10 to the minus 5, so that's 10 to the minus 4. And after rehabilitation, 9 10 to the minus 6, so that's 10 to the minus 5. The numbers are not exact. What's important is the order of the size of this exponent. Tells you to use to compare to other things. But just to compare what was the danger of having a failure due to internal erosion, and this is compared to the entire database of ICOL, and then we added the FEL when he came out with this book in 2015. He has some great data in there. And before rehabilitation, we calculated 10 to the minus 4, and lo and behold, it's what has been observed in the United States for a number of different dams. It's a bit lower than what FEL has compiled many more cases than the ICOL data here. And then after the rehabilitation, the probability of failure, the error probability of failure is significantly reduced. It went from here to here. Now, it's not my job to tell the dam owner that it's safe. He's the one who makes the decision when he needs to reduce the safety factor. But in this case, here's a picture of the dam. Just to remind, there's a big dam and there's 5 other smaller dams, whereas one of them is concrete. And then when you use this diagram, which you've seen before with the gray area, the main dam, the calculated failure probability before remediation looked like this. So this total in black is quite high. We're at 10 to minus 4, and we're in the middle of the guidelines. That's not necessarily a comfortable situation for a dam owner. He would like to be the water. So that's why we look at the effective radiation measure. But before we do that, that's the main dam. There were 5 saddle dams, and here's the numbers for 2 of the saddle dams. And then through discussions, we were looking at that, the authorities had required that every dam be raised by 2 meters, no matter what, no reason. And you know, if you raise a big dam, they're like 90-meter high meters, that costs a lot of money because you have to redo the slope also. And somebody said, yeah, but what if the saddle dam, which was oriented in another direction and had no consequence except the water flowing into a forest, which, okay, would inconvenience a few animals, but they would have time to escape, we think. And so that was part of the solution, is that, okay, we will do this saddle dam, it was saddle dam number 4, I think. We will make it to be programmed that as when a flood comes, the water raises, maybe raised, we will just let it fail by having it 2 meters lower. So it would be controlled release of the water. So it was a fuse plug. And here is the illustration of how the annual probability of failure change with the remediation, including a fuse plug. And before I come to the conclusion, there's a program in Norway, and I think in the past 8 years or 7 years, we must have analyzed about 30 different dams. Just the bigger one and the more susceptible to failure, there's a classification for that with a very rough analysis. So the Nation dam system, the analysis showed that the optimal solution was a control overtopping of saddle dam 4, the fuse plug, and during an extreme flood. Overtopping of saddle dam 4 reduced considerably the risk of a breach of the main dam. And it was so logical, but the authorities did not think of that. They said just raise all of that by 2 meters. So, for another dam called Vidalsvatn, it had evidence of internal erosion over 20 years. It was so much grout in that dam. And for the past 30 years, it had behaved correctly, but we were very unsure how all this grout in the dam behaved. It's become a new material. So there were 5 different remediation measures, including complete excavation with grouted material and different aspects, and also one of them was instrumenting so that you can measure leakage. The analysis quantified the risk reduction of several rehabilitation measures and showed that the most extensive and most expensive was not the one that was reducing the risk most. And so that helped the owner to make a decision. For a third dam, the Nyhedevatn dam, the reliability index or failure probability of the downstream slope suggested no need for rehabilitation, even if the traditional safety factor suggested it was 1.3 instead of the required 1.5, suggested a need for strengthening. And it's because they were selecting values of friction angle in the rock film, which were much more too conservative. Dragladalen, I'm sorry, all the funny name in Norwegian, but that's how I remember them. Something funny happened there. Is as we were analyzing, doing this traditional way, and then somebody passes a picture, a photograph, you have all the documents in the room, and it's in the middle of winter and there's no dam. Where's the dam? It's all covered by snow. And then one of the inspectors, the dam responsible who goes and look at them in the winter, he says, yes, and what happens in the winter? The ice goes into the tunnel or the spillway and it stays there until June. But our snow starts melting in March, and when it starts melting, it's very fast on the top mountains. And so we get all this water and the spillway is blocked. And so in this way, we identify, one could have done that without the risk assessment, but it was through discussion that suddenly they realized that there was a failure mode that they had never thought about. So this struck at ice and hard snow. So it resulted in an immediate rehabilitation, and then the new analysis showed that the probability of failure was greatly reduced from 10 to the minus 3 per year, which is too high, to about 10 to the minus 7. And Tam Kalhu is a concrete dam. That was interesting. There was a requirement that you should reinforce with this concrete plate in front of the dam. It's a funny form, old type of dam, buttressed, but a special design is done in Scandinavia, which are not built anymore. It's a very narrow dam. And so we did the analysis. And under the earthquake, the risk was increasing with all this stiffness applying everywhere in the dam. And that was a ha-ha for the authorities, that it's not everything you do that will reduce the risk. So the added value of these inventory analysis, it looks at all, if you're good, if you do a thorough job, at all potential failure modes in a systematic manner. It's very good to establish a diagnostic of what is important, what it is that increased the failure probability through all these steps in the tree. And it's a good tool to compare different dams in a portfolio and to prioritize which one should be handled first. And it has been coined as a systematic application of engineering judgment. I'm a great believer in engineering judgment. I think we should use it. And this was written in 2015 with a few modifications, but today the word à la mode is risk-informed decision-making. And that approach, which I don't talk too much about today is Norwegian, it recognizes the use of engineering judgment and that decisions cannot be made in the basis of technical data alone. And that is formalized in an ISO code on the risk-based analysis of geotechnical structures. So today, this is an accepted method that you will use engineering judgment in addition to all the other data that you have. Quickly, what happened with the New Orleans levees and what do the risk-based analysis tell us? If you remember, there was the Hurricane Katrina in 2005, and there's a Flood Control Act in 1965, and there was a flood protection system organized for hurricanes in New Orleans. And all of this is done by the U.S. Corps of Engineers. Serious work, they do good work. And this is one of the pictures of one of the breaches of the levees. There was something, the hurricanes, if I look at the history of hurricanes, they seem to be coming every 25 or 30 years. Although they call it a very rare hurricane, so it's not that rare. Could the failure have been expected better managed with the help of probabilistic analysis? So there's a bit of equation here, but when the levees are designed for a return period of 100 years, that means the probability of this hurricane coming is 0.01. But observation tells us it comes every 25 years. And so what is the probability of a 100-year hurricane and overtopping for a person living behind the levees for 50 years? You can do a small calculation with this equation with the Poisson distribution, and the calculation tells you that if you live there for 50 years, there's 40% that you will be affected by a hurricane with a return period of 100 years. If you use a return period of 200 years, 22%. So there's a significant probability, if you live there, of the levee being overtopped during the 50-year period and location. And the 3 or 4, it's not failure, but the hurricane that have occurred in New Orleans, even without overtopping, indicate the factor of safety is less than 1 in many locations. And in comparison, the dikes protecting the Netherlands are set to heights corresponding to about 2,000 to 10,000 year return period. So, and the Rhine we're using at 1,250 year return period. So we are using here 100-year return period. So, and to make things worse in New Orleans, there are 350 miles, so 560 kilometers of levees, and some of them are 1 kilometer long. So what is the annual probability of failure of each reach? And what is the probability of failure of the entire system? That we can always use statistics to calculate, and I will probably not go too much in details, but it's a function of the product of the probability, or the reverse, or the complement of the probability. And then the probability of at least one failure of the levee system. If you have 500 reaches, and they're 1 kilometer long, the probability that of the overtopping is 1%, and of the system it's 99%. There will be something that fails. And then you could take shorter reaches or longer, shorter reaches, fewer reaches and shorter reaches, and calculate, and the probabilities are very high. So it's certain that the next hurricane you will get a failure. And when something like that happened in New Orleans, they originally called it levees to protect people. You use the same FN plot that I mentioned before, and if you come here in a non-acceptable, then you reduce risk by reducing the consequence. Usually you evacuate people, or you try to reduce the probability of the hurricane happening. But that you cannot control, that will happen. So here is a diagram of the probability of failure of those levees in New Orleans. And first, in 2005, they called the system Hurricane Protection System. So people felt protected, but they're not protected. So in 2011, after Katrina, it's called Hurricane Storm Damage Risk Reduction System. It's psychological, but all of a sudden the government decided to protect itself, to protect itself in case of lawsuits. And this is the acceptable line that was the middle line in the previous graph. And in 2005, it was calculated what was the probability of failure and the number of casualties, and it was here. We know that 1,500 people died, so this was easy. But the only thing they could do, they could not raise the levees, they could not build better levees. They evacuated the people. So in 2011, after the evacuation was finished, there was maybe 150 people who were at risk or who could die based on the evaluation. So it's still unacceptable. We're much, much higher than this line. But they don't have a choice, so people are informed about that. And the most tragic about this is that the 1,500 people, maybe not exactly the same people, but the number of population is back to what it was before 2005. So we have the same risk today, we're back here as before. So this is probably so much you can do, but the risk, even after the 2011 upgrading, is much higher than what was considered tolerable for major dams in the world. What is the risk? Why is the risk so much higher for the levee system? So what was considered as tolerable risk, this is a new word for this lecture, but it's been in use for a long time, is not absolute, but is relative to the context of the cost, the feasibility of reducing the risk. And there doesn't seem to be, because of the foundation, to be a good solution for raising the levees. It was not feasible to achieve that lower risk for a long levee system in an urban area. And again, the statistical calculation say that it's nearly impossible to make this entire system safe. And maybe just one philosophical question, should one have used part of the $18 billion that we use on the measures to study and evacuate the people in advance of the storm? Should we use the money to be prepared rather than doing the solution after the fact, and then another lot of people would die? So the added value of the reliability analysis is that simple reliability-based analysis predict that the New Orleans levee would most probably fail under a strong hurricane. Long levees should be designed for very long return periods. Reliability analysis should be used to make decisions on the optimal mitigation measures. I see the time is passing, so I suggest that maybe I skip the calibration of safety factors, maybe just show you the last slide, but we calibrated codes for simple cases like this, a vertical load and a vertical or horizontal load, in order to find out what is the probability of failure for the same safety factors. I'll just go to the last drawing. For For the case of just a vertical load, no problem. But for the case of a shallow foundation on clay, undrained shear strength capacity, you have the three codes giving approximately the same probability of failure. But for a shallow foundation on sand, drain bearing capacity, the three codes gave very different probabilities of failures. And so that means that for the API code, the ISO code, and the API LRFT, load resistance factor design, is the partial safety factors. The required safety factor are very different. These are the required safety factors. They give very different probabilities of failures. In this case, for low uncertainty, 10 to the minus 4 per year, and in this case, 10 to the minus 3. And the situation gets even worse when you have high uncertainty in your parameters, and the failure probability gets very low, and you're using very different safety factors. Maybe I'll skip the conclusions, but I think it's very important to understand that the safety factor is just not the solution to all cases. Because the code gives a constant safety factor, but reality is you have very different cases, very different type of loadings, very different models, and then the failure probability is very different. So I'm coming to a few concluding aspects, challenge, emerging topics, and summary. And I think one of the biggest challenges is the communication, and being a good communicator is one of the most important skills when you're dealing with risk assessment. Because your client, he makes a decision, but then when he has to teach to the public, he asks me to do it. So it's not always easy for me, a nerd, a civil engineer, to go and talk to people who haven't been to school, who are a farmer, and explaining what is a probability of failure. But you know. And the quantitative assessment reveals that risk creating factors and the need of immediate change, and that's easy to talk about. You say, well, you see, yeah, if all of a sudden this slope fails in the reservoir, then it creates a big wave, then the water will start flowing. And if it's an embankment dam, it might get completely unraveled. If it's a concrete dam, no problem. And also, our role is important there, and we have a very difficult role because the geotechnical engineer we find in a vulnerable spot. We work at the interface of natural condition, rainfall, earthquakes, and man-made structures. And often we don't have enough information, and we have to use our judgment. So we're called to identify and define situations that are potentially hazardous, and to at least initiate a decision process and to whether the hazards are acceptable or not. So conclusions on reliability analysis: the approaches do not remove uncertainty, nor do they alleviate the need for judgment. They provide a way to quantify the uncertainties and to handle them consistently. The reliability approach also provides the basis for comparing alternatives. But we still have to do site investigation, laboratory tests, and all those aspects. But I find, at least in today too, is that the tools for risk-based and reliability assessment, they've reached a degree of maturity and that they're easy to use. You just have to get familiar with them. So they help you reduce the effect of uncertainties by quantifying them. So, and the uncertainties, in all geotechnical assessment, one needs to deal with uncertainties, either implicitly or explicitly, and see when one hasn't dealt with uncertainty, what happened here, the entire pillar of this on fire because of this landslide. There's a pillar here, and fortunately the truck stopped in time, and I will not tell the whole story. The people in the workshop got the whole story, but the farmer who owns this area, he did not think to consult the authorities or make a site investigation. He wanted to build a golf club because you earn a lot of money as owner of a golf club, but not as a farmer. So he asked his friend, who drives one of those mechanical, no, it's a grader, I think. And he started here, and as soon as he started, crack, crack, and then he gets transported down here. And I will not say more of the case now because of time, but it makes me conclude that deterministic analysis gave an impression of certainty, safety factor 1.5, and a moral certainty, 1.5, I'm safe, it's going to hold forever. Probabilistic analysis, they complete the picture by making explicit the uncertainties and their effects. And for improved geotechnical practice, we need to have both. And when I did the Rankine lecture, and so this was the first time the Rankine lecture was given by a woman, so it was number 55, so there had to be 54 men first, and then. At first I quoted something serious. I said, well, Voltaire said, doubt is an uncomfortable condition, but certainty is a ridiculous stand to have. So you have to admit that you have uncertainty. So that's good, that supported my theory. But then, because I was a woman, this is Kipling, he said, a woman's guess is much more accurate than a man's certainty. So that was the conclusion of Rankine. Do you want to have the career insights? We can skip it if there's no time.
No, let's...
I can speak for myself and the rest of the audience when I say we definitely want that.
It's not too long. Okay, career insight. How does a female engineer go from here, where she was born, spend half of her life there, and then is here to give you a lecture today. So what I'm going to say is my story a bit, as mentioned that I'm a woman, not that it made a big difference, and then what's a good career, and then try to give tips for your own story. And my credentials, I'm a senior civil engineer. I've been practicing for 50 years. I started young, just put that in. I'm Francophone, half Irish by my mother. I come from a very big family, so there's a great advantage in having 9 brothers. They tease me to death. And I come from a very small mining town. You never heard, I think, of it, Abitibi-Témiscamingue. But there's a mine at every second or third kilometer. It's just a marvelous country. And the mining and building construction of the roads, my father was a civil engineer, so he built the roads to get there. He was working for a contractor. And then I had a very normal childhood. And for my parents, education was the most important. Living in the boondocks like that, I was 5 years old, and my mother says, you're going to go to university, whatever career you want to have. And that was told to every child, boys and girls. Or there were only 2 girls. I was number 7 in the series, so I was not the leader type, I guess. And somebody made a characteristic of me, and I thought I'd tell you, I think maybe that's the most important. I am a female civil engineer who loves her work, and I think that's the secret of my whole career. I don't like to talk about myself. I like talking about Canada, Quebec, Norway. I love Australia, grammar. I did my bachelor's degree in literature first because my father wasn't sure that I was strong enough to be a civil engineer. I like to talk about NGI, our autochthones. These are the original Indians. Where I was born was a lot of what we used to call Eskimo and Indians. Now they call autochthone. I like to talk about clothes. I like fashion, books, films, knitting, embroidery, picking berries. And cats, bears, we had a bear, we had a wolf, skiing. I'm a nerd. So I never thought really or planned my career. I did not plan to continue graduate work. I had a job offer and I was saying yes when my advisor said, why don't you try going to MIT? I did not plan to become a faculty member at MIT. I never planned staying at NGI for that long, and I certainly did not plan becoming director of NGI, and certainly not staying on for over 20 years as director. And I did not plan on getting married for the first time at age 63. So, I don't know how come. So the lesson learned is do not overplan. The opportunities will pop up in your career. And just a few pictures. I come from this point A in Quebec. And this is what it looks like when you land. There's not much, a lot of flat trees. And then this is the gravel road to go to my home. It takes a couple of hours. And that's the mine in the city. At the time I was raised, there was the population of there were two cities. I'm in Miranda, and there's another city. The population was less than 10,000 people. And we live in a log cabin, just like everybody talks about Davy Crockett and such. We did that too. And then, but the winters were cold, so when my father got a lot of money, or enough money, never got a lot of money, then we were moving this house, which was closer to the mine. And you see, it's snow-rich country. You know, I own the house now because it's not sellable with 12 bedrooms. Who wants to buy it? And then this is how I look. And my brother teasing me again. I was, I don't know, 3 or 5. My first day of school, which was the happiest day of my life. All my brothers going to school and I could not go. Oh, I was so happy. And then I was very happy when I became a Girl Scout. And I'm a sport nerd, skating and skiing. And at age 40, I learned how to swim. Not before. This is when I went to Norway. And I'm afraid of water. I will try the pool at the hotel, but I'm afraid of water. So I never go anywhere close to water without this thing here. And then I grew up, so when I was at MIT. And so, believe it or not, I was in the miniskirt area. And I even got my degree with the hot pants, you know. But I was a serious lab person. This is at the lab in GI, and I was showing it to the King of Norway. And a field person, and I just love being in the field. That's the most recent picture, but I put that one just to show you how beautiful Norway is in the summer. It's Calhoun Dam. It's one of the dams that I mentioned. And my career path, my family had a strong influence. And anytime I get a prize, my brothers come, well, if it's in Canada, and they say, you know, she's good like that because we teased her and she knows how to live with men. And I think it's true. I was lucky enough to study at good school, not in Miranda, but I went to École Polytechnique, again at a very young age, and then MIT. And then I found that being exposed to different environments, rather than doing bachelor, master's, and doctor's degree in Montreal, I think by going at different universities and then you see being placed in other areas, it was very enriching for me. And then you find out that things are done differently, so you're not so stiff anymore. And I definitely believe that being a woman helped. So I was in academia, I'm consulting for 12 years. I was on the MIT faculty. And then I was seconded to Arden Associate, and then I was sent for 1.5 years in Holland. And I lived in Delft, working on Oosterschelde. I was on the closure, the last...
It all makes sense to me now.
And then I learned to speak Dutch. That will come back later. But you know, when I look back, I was active, I was young, I had lots of energy and such. So I became members of the Engineering Institute of Canada, the Canadian Society, the ASC in the United States, the International Society. And I got this big network because I was the only woman, essentially. And then people remembered. So when I was finished with tenure, all this stuff, I applied for the postdoc at NGI. The I is missing. Because it was called the Finishing School of Civil Mechanics by Rolf Peck. You know, so we say, oh yes, I know. I was in my 3rd year of engineering in Montreal. So if you have the chance to visit NGI, you know, it has this big laboratory and all this history. So I applied for 1 year, and I liked it so much. The way I liked the practical application, putting research into practice, and then the teamwork, the way they were organizing their project. So I started in GI in 1982, and as a permanent employee, as a normal person. And then I was seconded to Exxon in Houston to do some finite analysis because they were the only one with the Cray machine. And then I was seconded in 5 years in France for ELF that became Total, and that was consulting work and research. Managing director of NGI for 20 years. It was really a great period, but at the end I decided I had done enough budget and such. And so I've been working technically ever since. So what I thought I would, when I was about 25 years old, I thought I would continue as an academic, as a lab and in situ specialist, because that's what I was teaching. I would become more learned in this area and publish many papers. Like all the professors of MIT, they have a specialty and they publish on that the rest of their life. And then in the longer run, I would move back to Canada at the university. Well, that lasted until I left MIT to go to NGI. What happened technically is at NGI, the first thing they did, they sent, I could not speak Norwegian except minimum. They sent me on a dam up north as a controller and testing the core, the rock fill of the compaction because I was a lab person. And somehow I managed. They did not speak English and I did not speak Norwegian, but we managed somehow. And then I worked on cyclic behavior of sand, design of offshore installation, offshore site investigation, and then went on to the three-dimensional finite element. And so my doctor's thesis was on finite element. And offshore installation and dams, slope stability, risk and reliability. I started with that in about 1990. And then optimization in the lab. And so today, I work mainly in risk assessment and management for all geo aspects, also for tunnels, and as the people, the work that they heard for the safety of the Viking ships in the Norwegian Museum, and a lot on expert committee, which I very much enjoy. It was early for a woman to be engineer I started in 1967. But I never felt that being a woman made a difference. I don't know why. I think it's the way my parents educated us. I never thought that I was the only girl in the class. I don't know why. And since starting at École Polytechnique, I've never felt discriminated. There was discrimination in my hometown, of all places. The bishop, who was Catholic, there's a boys' school and a girls' school. And mathematics and physics and chemistry were only taught to the boys. And so my mother went and argued with the bishop that my daughter is as gifted as my son. She wants to study science. She has to be allowed to go to school. And after 2 years of fighting, I was allowed to go to the boys' school. So that was the only discrimination I experienced. So I was teased, challenged to be one of the gang, flirted with, but I was never put down. I like the presence of men, and I like, when younger, being flirted with. So I was fortunate enough. Yeah, I like men. I was fortunate enough to work with people who did not think that being a woman made a difference. And I was very sick at the age of 21, and I was operated on all that. And the boys, they took all the notes in class with carbon copy. They each take turns, and when I came back after about a month and a half, I had all the courses as a copy. You know, in those days there were no PowerPoint or anything. You had to take notes, and they did that without even me asking. I mean, this was marvelous. So there were some doors that were closed because I was a woman. In those early days, I was not allowed to go down a mine because I brought bad luck. And if there was a factory visit, the boss would come and say, "You didn't tell me there was a woman in the class?" And then he said, "She's going to distract all the workers." No. So then I was sent to sit back in the bus during the visit. But those are minor things. I mean, there were other opportunities. But I was not a fighter in the barricades for women's rights. In all circles, I was better remembered than my fellow male students, so that created an advantage. So I think I enjoyed reverse discrimination. So a good career? A good career in my mind is when you feel you are achieving something, when you are motivated to go about your task, and most importantly is when you're looking forward to go to work tomorrow. So you have to enjoy your work. And you can imagine, I did for my doctor's thesis every single drawing by hand. And I typed every single word on one of those typewriters. And you know, it has changed so much. And then I used a lot of correlation because there were not enough lab data. You know, those are plots of water content and shear strength. And today we're using machine learning and artificial intelligence to calibrate our strengths. So the career has changed so much. It's marvelous. So tips for your own career story. You know, I like inventories. I'm not going to explain. This is a very critical slope in Norway. So I've put the tips in the shape of an inventory. So if you have to seize the opportunity, this is between you and me, but in Norway, what I have experienced when I was director, some of our employees, maybe the Norwegian, not the foreigners, they were afraid to try a new field or to travel to Australia on a project. They preferred the comfort of home. But I found that if you were offered to move abroad, change, expand the topic of work, or take on new responsibilities, if you say no, okay, it stops, then nothing changes. If you say yes, you get new tasks, new network, and if you don't get any new tasks, then it stops. But if you have the new tasks, then the number of possibilities is infinite. And then be active in learning societies. I just listed, I'm a member, I think, in societies in 10 different countries, most of them where I worked a longer time. And even the University Alumni Association, it creates a network which is very useful. So again, in my inventory, this network for lifelong learning, new project, technical collaboration, congenial exchange. I really enjoy going to conferences and talking to people, not only about soil mechanics, but also other things, skiing, for example. So if you have a new network, the number of possibilities is endless. Naturally, some people in the new network are not useful, so then you just try to move to another group. And then if you have no network, it stops. And then finally, the third inventory in your career is I'm really convinced that I had more chance because I could speak many languages. So learn many languages. It's easy today with the Duolingo and all these things. And a secret is once you know two, or at least three, the others, they come by themselves because there's a logic in languages. It's just like mathematics. And so learn 2 or 3, and after that, the rest comes easy. So then, I'm the one who got all the projects in France when I was at NGI because I spoke French. I'm on several RTRBs because I speak French. There's not enough people speaking French. And then I'm making a workshop in Peru, but then I can speak Spanish, so then I can do it. You know, it opens so much doors, and it's not a big effort. It's easier to learn when you're a child, but that time is over, so just start is enough. Then more seriously is combine basic technical skills. I call that inventiveness for new solutions and knowing where to find ideas for new solutions. I'm not the most creative person in the world, but I know who I should consult to help me develop innovative solutions. Work in good teams and make your team look good. Know yourself and what you're best at. And I know I'm not the best theoreticians, but I have a lot of experience for lab testing, so I contribute in there and how it affects the finite element. That's important. Do not try too hard, the good opportunities will come. Unfortunately, I see today at NGI, nowhere in Australia, some younger people, they're much too eager and they walk on other people's feelings just in order to advance themselves. And that doesn't work. So we have a problem right now which we're trying to solve. It's a woman, but you know, she is so eager to be at the forefront of everything, but she's so young. I mean, so you have to be careful with that. And people skills, effective communication, and interpersonalities, that was not important when I graduated. Today it is important. And the commitment to lifelong learning, 20 years experience is important, but not 20 times the 1 year experience. There's a difference there. So don't do the same thing. And then today we have to be aware of societal changes. And I say that it's important that you show a passion for what you do, maintain a curiosity to learn more, and learn from your errors and the errors, especially the errors of others. You never like to make an error yourself. And computer programs. They're very dangerous. So understand the basic assumption that underlies the software you're using. And it's Mike Duncan who said, doing a simple study like this, you should always use two different programs. And I think that's very wise. Ensure redundancy, and I think publishing your work is also important, and it's not easy, and I think most of my papers I have written on my own time. I've never had, and now I have some clients that pay my hours to write a paper for ICO because they want to have a presence. And then last presentation, you should think more about what the audience wants to hear and not what you want to say. So, and then I'm getting close to the end, is do not overplan your career. Rather seize the opportunity when they come. And I'm convinced if you offer two different things, one is to be sent to Holland and the other is to become head of your section in Canada, they're both good. But once you make the choice, devote yourself completely to it and it will go well. And a good health is indispensable. I don't think I could have done what I've done. I work very hard. I'm a nerd. So it's important to take good care of yourself. And I perceive, I work mainly with young people now, very young people, and I perceive that this generation is much more capable and having a much wider background than what we had in our generation. So I think the future for you people is great. And then I have this one reflection before my conclusion is, what about when you have become an older geoprofessional? I never thought I would become an old geotechnical professional, but at one lecture in Norway I was introduced as the grand old dame of geotechniques. It's my grand old dame, it's like somebody 100 years old. Well, first, for me at least, you never realize that you are 75 years old. You think that you're still the same young person, and you're able to do the same as before. And as long as I can, I will continue walking on dams. As long as I can follow the men, I'm happy. But what I do enjoy most is working with the young geoprofessional, because they have all kinds of ideas and all this enthusiasm, and that's very rewarding. And then I can come with a few things with my experience. And I do enjoy not having to do all this administrative work I used to do before. And perhaps the only regret is not having been an academic for a longer time. As you could see, I enjoy lecturing. I've always enjoyed teaching, and the contact with younger people keeps you younger than what I do now, is running from one project to the other. So, continuing thought is, looking back, I don't think I could have been happier in any other profession. I considered becoming, I went to Polytechnique thinking I would be a chemical engineer, but civil was more interesting at that time. The engineering and geo profession is really very special. It's friendly, it's proud, it's devoted to continuing improvement and continuing renewing itself. Just think of what's happening with all the digitalization today. It's the interaction with colleagues and clients, and more recently for me with the public because of this risk assessment part, that is the most rewarding. And I get a lot of jobs for NGI, but nothing replaces the enthusiasm when trying to convince a client. At least that's what the client tell me. Well, he said, well, you're so excited about the project, and we cannot say anything but yes. So success is not synonym with higher salary, a fancy title, or higher international recognition. Success is gaining the respect of your peers, and that's very nice when I feel the people in NGI, they look up to me. Unfortunately, they look up so much to me that when I turned 75, they put it everywhere on the internet. And then everybody was sending me congratulations. I said, well, my clients don't know I'm 75. They're not going to hire me anymore. But in Norway, celebrating round birthdays, the 5s and the 10s, is very important. So I'm terminating this question of different jobs at NGI, and it's difficult to see, but there's Terzaghi having lunch with a bottle of whiskey, which today would not be accepted, but these are the type of jobs we do. But NGI is the people. And Ida, Shansley, and Guillermo are the ones who started GI. And here, there's Queen Elizabeth visiting us, and my husband, who was director then, and then a lot of our employees, which you can see. And I have to show you our fabulous laboratory. Enjoy your career, seize the opportunities, and you will achieve amazing results. Thank you very much.